can I go and get
Yeah, yeah.
tea?
Yeah.
It was like started from back-to-back meetings at full day. It takes a toll. Se on kuitenkin tilanne, niin täällä ei ole ketään muuta kuin työ. Mutta me sitten silti täällä takapenkillä. Eli onko se niinku, periaate on periaate.
Laaja näkymä tähän asiaan.
Kyllä. Periaate on periaate, etupenkki ei mene. Few more minutes. Um,
I've already turned that.
is it on?
I've turned that on.
What is that protector too? Because I think that there's only one
Yes,
in this place. Saying nothing.
should we turn it off or on? No, it's on. In the meantime, is the camera okay? The location and everything.
Okay, let's take a look. How do I look today?
Strong as ever.
How about young? You look young too? I don't feel so today because I'm really beat it today. It's been a little bit too rough day.
We don't do that
Absolutely right. Look at me. I started to explain something nonsense. Now, when you said, like, okay, get back to reality, I realized that I feel strong. It's okay. It looks very good. It's perfect background again. Very good. Okay. Okay, I think we're good. So I think that I want to go this fast as I can. So it's
And
gonna be.
I believe people mostly are taking it online.
Yeah, I know, I know. So only team left is Team Finland. All others are no longer here. Okay. Hey, thanks, Mustafa. I think it is
By
okay.
the way, like there are a few small things that I want to discuss with you. Is it okay if I just
Like
talk to
after
you
the
after
lecture,
this?
can we take a look at this whole thing about the lecture? So
Yeah, I
briefly,
will be here.
briefly.
Okay.
So should we have it in telemeetings or because otherwise I cannot see your screen?
Yes.
You prefer tele?
Because otherwise, how can I show it? Either you
Yeah,
have to
yeah,
go to
yeah,
the
yeah.
office or yeah.
Okay, so can we have it right after we close this
Yes,
one?
yes. Okay,
That
if
makes
it's
sense.
okay with you,
Yeah,
because
it's okay. Okay. Okay.
see you.
See you. I was very worried about you guys, like where you are. Finally, you came, so we're ready to get started. Okay. Okay, we'll see how we're gonna do it in class quizzes because there's less people in class. I mean, here in the physical class than in the previous times. Okay, guys, look at this. Look at this. What do you say when you do this? Correct. Respect. Respect. Okay. It's quite amazing. We met not long ago. Are we always ready to wrap up this course? It's quite amazing. It's amazing thing. And I realized that yesterday when I was looking the lectures, like, oh my God, is it really so that after today's lecture there's only 3 more lectures to go? Like 3 more lectures to go. Is it really the case like that? And it seems so. But because I love you guys so much, I don't know if the feeling is other way around, but I love you so much. I'm thinking that what if I'm gonna give you extra lecture, which is not gonna be a part of the midterm exam, but something that I feel that is my responsibility to tell you, and something that I feel is my responsibility to tell you is a career counseling. How you like about that? Career counseling that touches 2 subject matters, your life and career, and then the detail, which is related to your life and career, which is a master thesis topic. How you can select the master thesis topic, what are the practicalities related to that, what are the good practicalities related to your master thesis project, what makes sense, what makes not sense to do, and stuff like that. So I really would love to give a lecture like that. It's not technical subject matter. It's about my perspective of life and science and master thesis projects. So if you want, I can do that. It's up to you. Up to you. I don't see if there's any comments from online participants if they would like to see it or not, but it's not going to be mandatory. So if you feel that you're busy, don't come. If you feel that this is something that could be beneficial in your life, please come. I feel that particularly the ones that are international students, it would be beneficial to know a few tricks how to squeeze yourself into the Finnish companies if you desire to go to industry. And if you desire to stay in academia, again, what are the tricks that make sense to do? All right. I don't see you guys are like, I don't know, it's maybe enough for Aki, but let me think about this and we'll get back to you next week. Okay? So it's up to you. If you want, we can do it. If you are not busy, we can skip that. All right, what's going to happen today? We're going to jump into the real deal of the modeling of hydraulics. Something that is very, very, very important today is alarm fluid theory. So this will be the basis of the hydraulic modeling. This is going to be the differential equation that tells you how is a pressure in any given time. how you can compute the pressure using the first order differential equation. That's what we're going to discuss today. Also, we're going to discuss about something which is called discretization. Discretization is a procedure, is a concept that you have been using whenever you're using the strength of materials like finite time method. You're discretizing your structure to small elements. Here too, when you're using line fluid theory, you're kind of discretizing your hydraulic circuit to certain areas where you can actually compute the pressures. And how you do this discretization, what's the concept behind, that's something we're going to discuss today. Okay, and that's going to be something that is extremely important you to understand the concept and how is a differential equation that describes the pressure. That's what we're going to do today. And I think if we have a time, we're going to discuss a little bit about the flow types. But honestly, maybe not. And it's not about the time matter, but it's more about, today being a rough day. It's been a back-to-back meeting since this time. Finally, I can focus on this one thing only. But it's a little bit of low energy. And Mustafa is going to be angry when I say it, because usually when he's asking like how I'm doing, I say that either I'm feeling very strong or super strong. Those are the two things. But today I'm only very strong, not super strong. So that's why we might have a lecture a little shorter than usual. Okay, but before that, let's look what we discussed a week ago. So a week ago we opened the topic of properties of fluid. And we realized that there are two things that are important. There's viscosity, which is not important. And then the bulk modulus, that is actually really important. And the bulk modulus is something that describes the flexibility of fluid. So if you take a hydraulic cylinder, you press it, you compress it, yes, the piston actually is moving within the cylinder. And this flexibility, in some cases, is more significant than the flexibility that comes from the mechanical structures. The mechanical flexibility, the structures that are capable to deform. Where's my stick today? Here. Like structures that deforms like this stick. This is something that I'm planning to discuss about that in the second last lecture of this class. A little bit about, for your information, how you can make this to happen, how you can model deformable bodies. Right, so I was about to say that sometimes the flexibility of hydraulics is more significant than the flexibility that comes from the mechanical components. Most of the harvester cranes, like the lift arms and such, they are examples of the system where the flexibility is mainly coming from the hydraulics, not from the mechanical components. Okay, but the viscosity is only important if you have a laminar flow. We discussed about the bulk modulus. We completed this by first looking at the unit size container. And we realized that what is a bulk modulus? It's a ratio between the pressure difference versus the volume difference. And as the volume is getting smaller, the pressure is getting bigger, the volume is here minus in the size. So this is what it is. And when you try to kind of generalize this to any size of the volumes, and when you take a multiple volumes simultaneously into account, then you can compute something that is called effective bulk modulus. Effective bulk modulus, it takes all the sources of flexibility into account. And you can compute that in case like two containers that are shown in this figure, in a way that you first take into account the flexibility of the fluid. This is something that in reality is a function of pressure and temperature too, but it's very often assumed to be constant value. So it's going to be 1,500 megapascal, which is a typical amount of bulk modulus that is being used in simulators. Then you have the next component, which is a size of the volume 1 versus the entire volume of the system you look at. Entire volume is going to be volume 1 plus volume 2. Right, and then you're going to take this flexibility of the first container into account. If it is a steel-made container, like a hydraulic cylinder, you can make an assumption by using this very simple equation where you have here diameter of your cylinder, wall thickness, and the elastic modulus. This is going to give you a rough estimate about the flexibility of your container. Okay? Then you have a second container, so you can do the same. And then finally, you have here how much you have dissolved air. This is the hard component to estimate because in reality, it's almost impossible to know how much exactly you have dissolved air in your system. But this is something that you can give a shot and try how much is making an effect. And one thing that is not mentioned here, if this, let's say this container is not steel made, but is like rubber hose, that is typically the one that is reducing the effective bulk modulus very significantly. And here was an example how much exactly that is reducing. This experiment is such that this y-axis here is effective bulk modulus. But look at the numbers. So this is a megapascal, and this is like 800, 480 megapascal, so it's reducing quite significantly. And this is because of the hoses itself. Hoses, even though that they have a steel net, they're introducing quite a bit of flexibility of the system. And if you have a desire to make your hydraulics to be more rigid, the one simple way to solve the problem is to reduce the hose lengths. This is one thing that helps you. Sometimes you need to play a little bit about, the Aiken frequency associated to hydraulics to make sure that they don't go along, same region than natural frequency of mechanical structures. Then you can play with the hoses and so on and so forth. Yes, sir.
Do you ever want like a bouncy system?
Do I have what?
Do you ever want like a bouncy system with like with low modulus?
Low bulk modulus.
Yeah.
So when I can meet the low bulk modulus?
Yeah.
So when that happened?
When you want, is it ever wanted?
Ah, that's a good question. Yeah, that's a good question. Okay, here's the thing. So you might have a system like this. I get emotional here because we have communication. We have a great level of friendship here, do we? No hugging. I keep it at level, but it's a fantastic question. Okay, so if you might have a system like this, so let me put it here. So if you have like simple crane like this, you have a mass at the end, and then you have a cylinder here. This is your hydraulic cylinder. All right, so because of the flexibility of this mechanical component, you could simplify this structure in the sense that you have like a hydraulic cylinder, and then you have a spring here and the mass. Okay? Now, actually, when you look at this hydraulic cylinder, the hydraulic cylinder would be something I'm going to make one more drawing here. This is going to be the mass. Then there's a spring. This is a mechanical spring. This is what comes from the flexibility of this simply supported beam. Okay? And then you have here a hydraulic cylinder. Let me describe the hydraulic cylinder like in a way that there is actually a piston, and this fluid here is a spring. And here there's another spring. Now this is a one flexibility as a total that is coming from hydraulics. And this is the one that is coming from mechanical component. Now the big problem could happen if the frequency of the hydraulics is in the same area, same neighborhood than the frequency of the mechanical flexibility. So one needs to go another place. So which one can go? Okay, so flexibility of the mechanical structure, probably there's nothing you can do about that anymore because it's already structure that is existing, so you cannot touch that. Okay, so the one needs to go, one needs to move away because they don't get along well if they're in the same region. So one that needs to go away is the hydraulics. So what you can do for hydraulics, you can either increase the flexibility or decrease the flexibility. Increase in flexibility comes with a certain number of limitations because you might be the case already that you have no longer hoses, but the pipes. You have tried to get rid of the dissolved air as much as possible, so it's no longer in a pellet, but still the frequency is not good. So maybe you can then reduce it. And if you reduce it, because the frequency that comes from the hydraulics is typically in a range of, let's say, 10 to 50 hertz. This is how much it is a frequency. So if you're in the upper level of this range, you might want to go down to make sure that you're not aligned with the mechanical frequency. Fantastic question. Nice. Yeah, so this is how it goes. And it is actually the case that if you have a two-way cylinder like this, there are springs in both sides of the piston, both sides. And what matters too is the hose lines that can affect the flexibility. How you can compute the natural frequency of a system like this, we're going to take a look at that momentarily. Very good. Good stuff. So was it like a moment, just a short moment of time when we have this friendship and now we're back where we were? Oh my God, yes. Yes, sir.
On that matter, how about for something like a
Hydraulic brake system?
hard either, do you?
Hydraulic brake system, like you mean like vehicles?
Like, for example, a bicycle.
Bicycle. Okay, so what about the pressure? So you're asking about the flexibility of the braking system,
Yeah,
hydraulic brakes.
yeah.
So do we want to reduce that, or so you mean the natural frequency associated to that?
I mean, I guess you'd want it to be in a certain range. You don't want to be too hard or too soft,
Right,
especially if you want to reduce maybe the sticking of it, like the anti-blocking system as well.
right. My experience is this. So I'm going to tell these to online participants. So the question was related to hydraulic brakes. Bicycle is an example. In a bicycle, what happens is that you have like a piston in this side, and then you have a hose line which is of course still that hose line that goes all the way to caliper, and the caliper you have a pistons that are moving the braking pads. And the question is that should that be flexible or rigid? And of course, because I'm very close to be a professional cyclist, downhill cyclist, so it's only a few clicks that separates me from the professional cyclist. I prefer to brake that is as stiff as possible. And why as stiff as possible? Because if there's any dissolved air, you know how it feels in the brakes. It feels that you don't have a clear sensing when it's actually braking. You don't recognize it so well. But when it is as stiff as possible, then it really is feeling that your finger, you can control the braking as good as possible. But I think your question was related to ABS systems. So to make sure that they don't get locked. I think there too, what happens and what helps is that if you have the hose system and hydraulic system as stiff as possible, because stiff means that you have shorter reaction time. If there's a high level of flexibility, there's a certain amount of delay because of the flexibility itself. That's my way of thinking. I don't know if you guys agree with this.
But I've seen some, I don't know how they work, but anti-blocking systems, mechanical ones on bicycles.
Really?
I've never cut one open to see how it works, but
So, not locking, the brakes that are not locking in a bicycle.
yeah.
Really? So it must be something very recent thing.
I mean, it's definitely not the same as in a car because there's no electronics or anything.
Yeah, right. But
It's
the
something to do with the
mechanical
mechanics
thing.
inside it.
Right. Yeah. But in a cycling, sometimes you just need to lock your rear wheel. Just you need to do it just to maybe to turning your bike. So you want to have this ability that you can close your brakes like completely.
I was on a road bike, so
Oh, road bikes. Oh, yeah. Yeah, that's what I don't do. So I'm not in a professional level in a road biking, so don't know that in details. So it's only mountain biking that I'm very good at.
and you don't ever want to lock the front wheel.
Yeah, not really, but you can sometimes want to brake really hard, like really in a level that is almost like braking, almost in that level. Oh my God, we even touches the subject matter that I like the most, this biking thing. Really nice. Let's look at the natural frequency business a little bit. Okay, so let's go back to this example we looked a little while ago with the difference that now there is no mechanical spring. This is just a mass that is top of the hydraulic cylinder. So this is almost like an example we looked a little while ago, with an exception that now this mechanical flexibility is assumed to be non-existing. So it's only the flexibility that comes with the hydraulics. Now, how is it you can compute the natural frequency of the system like this? The natural frequency is always a relation between the stiffness and the mass. All right? Stiffness, we need to figure it out one way or another. Mass is going to be very simple in this case because here it is. This is our mass. So only thing we need to figure it out, how is the stiffness? Okay, we know that the bulk modulus is closely related to stiffness. How we can compute this in a way that it actually is a spring coefficient, the way that it is needed in this equation to compute the natural frequency. Okay, stiffness, we know that is a difference between the force and the displacement. That's the definition of stiffness. Okay, so if it is about the difference of force and the displacement, let's take a look at how we can compute the force changes, how we can change the force in this system. And now it comes something that I have not explained you earlier, but it's good you to be aware of that force produced by this cylinder will be computed in a way that there's a force that tries to push this upwards. This force is going to be the pressure applying in the piston side multiplied by corresponding cross-section area. That's going to be the force that is moving the system this direction. Okay, so this force is simply P2 multiplied by A2. There's a force that is fighting against. And the force that is fighting against is going to be the force here and the pressure that is applying in a piston rod side. Now the piston rod side in a cross-section perspective is a little smaller than the piston side, but still there's a force that is fighting against. How much is a force that is fighting against? Is of course again the pressure P1 multiplied by corresponding cross-section area. So the net force is actually going to be P2 minus P1. What are the components we can change here? We cannot change the cross-section area. I mean, okay, let's say that what we can easily change. We could change the cross-section area, but then you need to get the mechanical manufacturing. That's not going to be easy thing to do. But easy thing to do is, of course, this guy, pressure. That's something that can be changed. Okay, this is going to be our force change. Displacement change. Well, this is going to be simple because we know that the volume change is related to where is the piston position. So if you know the piston position, you can compute the volume change. Okay, now we have that too. Now we simply substitute that information here. We take this displacement change, we're going to put it here. And the stiffness can be written like this. And now comes something important for us, something very, very critical for us. So we're going to make a use of the definition of bulk modulus. Okay? Once we make a use of the bulk modulus and using this equation which says like this is also coming from the bulk modulus. So we can substitute this inside of this equation and we can compute the stiffness as it is shown here. Now, here is the effective bulk modulus, the one that describes the flexibility. Then I have here cross-section area that corresponds to the piston rod side, and then there's a cross-section area that corresponds to the piston side and the corresponding volumes. This is how you can compute the stiffness. And that's how you can compute the flexibility. So you simply take this one here, the one we computed, put it here, take a square root, and you can compute the natural frequency of the system. This is going to be, by the way, your weekly assignment from 1 week from now. So you need to compute something. Let me explain. You need to compute this structure where you are assuming there's a mass, where you're assuming this mechanical structure to be completely rigid. No deformation whatsoever, but you need to keep in mind that there's a level arm because the mass is a little off from where this can rotate. You take that into account. I think that the length was 1 meter, if I remember correctly, and this was 0.1 meter. So the mass is going to be feeling here 10 times bigger than otherwise it would be because of the level arm. Okay, here's my question to you. First in class quiz. Bulk modulus in hydraulics describe force produced by a cylinder, flexibility, compressibility of hydraulics, oil amount in a circuit, number of components in hydraulic circuit. One only is correct, but which one is correct? So what says our YouTube, not YouTube, but the WhatsApp officer, is that the WhatsApp going hot?
Not yet.
Not yet. No one is saying anything in the WhatsApp. Are they saying? Are they saying what is that the WhatsApp community is voting for? B. So they're voting for B. So somebody has a high level of self-confidence that they are voting for B and put this in like visible for other students. Okay? Can you think about this a little while and we get back to this momentarily? Okay? All right. One thing that I did not mention when I started a week ago, the hydraulics. The one thing that I did not mention that is extremely important you to understand the drawing symbols of hydraulic components. I assume that this is all clear to you. But if not, this is going to be a little difficult to you. We don't touch that many components. But when we're saying hydraulic cylinder, which physically look like this, we're making a drawing symbol like this. And when we are looking at like a direction valve that is physically looking like this, we're going to use a drawing symbol like this. These are the symbol throttles. They look like drawing symbols like this. And this is a pressure relief valve. Pressure relief valve is going to be this guy here. Pump looking physically like this. Drawing symbol like this. Motor is looking like this. Is this one. Okay, so that's what we're going to play the game. So we don't show how they physically look like, but instead we're using these drawing symbols. Okay, shouldn't be too difficult. And if you're feeling shy about that, you can take a look at any literature of hydraulics you want. And it's all become clear like no time at all. Okay, the last thing that we need to touch, and then we're moving on, the most important subject matter in the hydraulics. So the last thing is a viscosity. Not important. Why? Because like I mentioned earlier, the viscosity only comes into play when you have a small pressure differences through the orifice, through the throttle, which is not common, particularly in the mobile machinery, mobile hydraulics, the pressure differences are lots, for sure more than 10 bars. And then it's safe to assume that the flow type is going to be turbulent flow, not the laminar flow. But we're going to touch the different flow types later in my class, if not today, then next week. All right. Here I have an experiment. So I have a setup where I have a plate. Plate is the one that is wide in the collar, this one here. And I'm moving this plate by using the force F. And because of the force, this plate goes with the constant velocity. The constant velocity is a V here, this one. And it goes off from the rigid surface. The rigid surface is this one here. This is one that is standing still. Now, what is between the rigid surface and the plate that is moving with the constant velocity is a oil film. Oil film, which is assumed to be behaving like Newtonian fluids. Newtonian fluids is something that, when you take a close look about particles, again, particles, our best friend ever, particles, fluid particles this time, not the mechanical component particles. The particles that are next to the plate having the same velocity than the plate itself. So they're kind of like riding together with the plate. But you need to be very close to the plate to make that to happen. Then fluid particles that are next to the standing plate are not moving at all. So they are standing still. Rest of the particles that are between this fluid volume of the fluid film, thin layer of oil, which is denoted as a Y, they are linearly distributed. So the one that is in the middle is going to be this speed divided by 2, and so on and so forth. So that's how they are assumed to be behaving. Okay. Now what we're going to do is that when we start to look at the closure, we're going to pay a close look about the force itself. And of course, the force that is needed is coming from this equation. And this equation, I have cross-section of the plate. Then I have the velocity that I'm running. And how far, no, this is better to say how thick is my fluid layer here. How much I have fluid between these two objects. The one that is standing still and the one that is moving with the velocity way. And something that is additional component in my equation is an absolute Well, absolute viscosity. And this absolute viscosity describes the friction property. It's like pretty much like how much this fluid is collaborating with you. You understand that if you need to use a very little force, then the fluid is something that is collaborating with you. It's not resisting much about the motion. Whereas if it is, you know, very, very high, it's like very thick material, then you need to use a lot of force to drag this plate in a certain velocity because the particles and this viscosity is fighting against you. It's trying to resist the speed as much as they can. This one here is a viscosity. That's what we're looking for. And now when we're looking for the viscosity, typically we are simplifying this equation in a way that we're getting rid of the cross-section of the plate and the force itself. And that can be made by using the shear force. This is coming from the strength of structures like copy-paste. Shear force definition is, shear force strain is like force divided by cross-section. When you do that, then you can write it like this. Now, absolute viscosity is not being used. This is something that you don't really find in the literature. So typically, what is being used is something called kinematic viscosity. The kinematic viscosity you can get by dividing your absolute viscosity by density of your fluid. That's something that we can actually use. You're going to see later today that once you have a different kind of the trillings, different kind of trousers, this component is the one that is being used here. So it's kinematic viscosity. Kinematic viscosity, when you're using SI units, is a meter power 2 divided by seconds. Often not used. You wanted to get the new oils, your car, your braking system. I'm not sure about the braking system, but at least if you want to change the oil in your car, typically you look at this viscosity by using something that is coming from Society of Automobile Engineering, American Society, and they are using this kind of like psi that are associated to these SI units as it is on here. But this is the one that is very common. Like when they say, okay, I want to get the oil from 0 to 30 or something, so they're referring this Society of Automobile Engineering. But when you do the simulation, then better, of course, you use SI units. This unit something we're going to discuss a little later. It's a little bit of headache in the modeling of hydraulics. All right, viscosity, heavily dependent on temperature. You see here is that there is an example. So this is how much the viscosity is dropping, and this is even in a logarithmic scale, because otherwise you cannot even display so well. So when the temperature is moving from -20 to 100 degrees. So that's why those one of you that are doing the car racing or something, you need to make sure that your engine is warm, because the viscosity of the oil is changing radically depending on the temperature. Once the engine is warm enough, then you can do this famous put the pedal to the metal. I'm sure you heard this before. Okay. All right. So this is it. And now comes this law of fluid theory. Any questions? Anything you want to discuss about modulus, about this spring coefficients or viscosity? Or should we take a look at the law of fluid theory and then discuss? Or should we take a look at the in-class quizzes, how we're doing in that? Is it going to be, or is it not? So it's going to be 100%. I hope not. I hope not. It's getting late, so I don't want to call direct at this time of the day. But one thing that I'm very much interested in, this is what I'm mainly interested in, how many participants we got. Okay, discard. And you don't see this again. I'm going to put this back momentarily. Major drop. So we came down from 120, was it 130 students to 115 students. What's up this week? Is it something special going on this week? Is what? Come on. So these guys in a class are saying because of the snow. If this is a reason not to study, the Finland is not a good place to study. I can tell you that. So regardless of the weather condition, you always come because you said that no, it's an unpleasant weather. I cannot study. Oh my God. Is what? Guys. So yeah, look, the next time you're gonna see a sun, it's gonna be. I can tell you, it's gonna be March. And yeah, seriously, seriously. And then once you see this, like you're gonna, many of the new students they're calling to this 911, which in Europe is not the 911. They're like, what the heck is this thing out there in the sky? Answer is this sun. It's sun. Take it easy. Yeah. So it's because it's not gonna happen that often. From this on, we're gonna dive in. So the daylight is getting short rapidly, very rapidly. Okay, success rate is gonna be what? 90. It's gonna be 100. Yes, sir. It's gonna be 100 today. So, so let me make my call ready to the Juhis. Oh my God! No, I can't. I cannot do this. Should I give him a call? Okay. Oof. So he will be available for sure. Okay. So can I call him using the WhatsApp? Because in a WhatsApp there's a camera thing. I can try to do this. Oh my God! I don't know if this is a good thing. Okay. So let's see if this is gonna work out. I am in middle of class and my students would like to say you something. Okay, so I say, can I call? I'm in the middle of the class and my students would like to say you something. It's delivered. It is delivered, but I don't know if it is, if he's taking, if he can. Okay, so let's wait if he see the message. Not yet read it. Okay, so we continue as soon as I see that he's been seeing this message. I'm gonna give him a video call. Yeah, because of where is it now? Because of this, of course, to show that okay, we are able to score 100%. All right, ready? Ready for that? Still not. Do you think of how he's going to take this? He's going to be happy to see good student, high-level students. Okay, so this is where I need to put this back. Not this. Okay, line fluid theory. Line fluid theory. I think it would be quite a bit of fun. I don't know. Maybe I'm too bold to say that it's quite a bit of fun to call the rector because maybe he's not going to like to get the calls, because it's no longer office hours. So it's 4 o'clock is when the office hours are ending in Finland. Okay, line fluid theory. That's the core of the modeling. That's what we really need to look at when we really wanted to model the hydraulics. And this is a good method. It's a relatively simple, is quite accurate, but it cannot take acoustic waves into account. That happens sometimes if you have a very rapid hydraulics that is capable to open and close throttles like very, very rapidly. If this is going to be, I don't know if this is him or not. I think I'm not going to take this phone call, but I'm going to call him back once we have a break. Okay. So in mobile machines, the pipelines are typically quite short. Work cycles are relatively slow. This is no longer valid because remember I said that there's something which is called digital hydraulics. Digital hydraulics changed the game a little bit. So not too much change in the game, but it's something that is, there's a possibility of acoustic waves. So what is these waves? It's like basically what we discussed earlier. So if I'm speaking here, what happens, the waves are traveling from my mouth to your understanding system, your brains, and this is because of the waves. The same kind of waves can take a place in a hydraulics. So when you stop something very rapidly, these fluid waves can travel back and forth, these pressure waves, but typical things are happen slowly. When you do that, the waves are not there, so the vibration is not happening within the fluid. But in theory, this is something that can happen. This method, not able to capture it. Okay, how it goes. So it goes like I said earlier. So we can form differential equations that describe each of the volumes. And what you need to do in the beginning, you need to divide your hydraulic circuit volumes to volumes. And how you do that? You do that in a way that you are assuming that in a certain area of your hydraulic circuits, the pressure is equally distributed. Because in this area, you're comparing the pressure using one differential equation only. So that's where the assumption is actually coming from. It's quite natural. This selection, this discretization procedure is not very complicated. It's actually very straightforward when you look at this back. Now, each of the volumes are separated by throttles or other different kind of components. Actually, it doesn't matter what kind of components we're looking at. We're always assuming that there's like a simple adjustable throttle that differentiates one volume from another. So that's the way it goes. And I'm momentarily going to show you the examples. All the components, direction, pressure, flow valves are assumed to be throttles, variable throttles that are changing their diameters based on function of different kind. That's the concept behind. And we're going to practice this multiple times. Here's a damper, fluid damper, where there's two containers. The container that is in lower side and upper side. And the question is that can we assume that the pressure here is same than here? No, we cannot. Because what's going to happen if you take a hold of, first of all, you take this damper body, attach that to ground, you press this downwards. What will happen is that the pressure here started to increase. All right? Pressure here started to decrease. And then what happened because of the pressure difference? There's a drilling that connects these different volumes together. The flow started to equalize the pressure difference, and it's doing that with a certain delay. But if I press it like hard as much as I can, there's a pressure difference. The pressure difference causes the fact that I have to compute the pressure here in the lower side and upper side separately, because it's not the fair assumption to say that the pressure all the time is constant in both sides. They will eventually be the same because of the drilling here that try to equalize the pressure difference. But because of the inertia of the system, because of the delay, it happens not immediately, but after a little while. All right? So it means that in discretization of a system like that, you have to discretize the damper in such a way that two volumes. There are two volumes, the one that is here in the lower side and the one that is here in the upper side. Makes sense? Then they are not disconnected, but instead they are connected. And they are connected because of the drilling here. And this is actually how the damping system, of course, it's not the simple drilling, but it's like a shimming system where there's a deformable plates and everything. That's how the dampers are actually working. The shimming system is quite complicated, but basically that's the way it works. So the drilling here is a throttle, and the flow try to equalize the pressure difference. How much is the flow? Depends on the pressure difference. Pressure difference depending how big it is, can have a two different. I mean, the flow can have a two different types: laminar flow or turbulent flow. Typically, when we are looking at the things, it's going to be a turbulent flow, and then the viscosity has no role whatsoever. Makes sense? You're still with me? Okay. So let's continue then. What about this? Now I have a little bit of more complicated hydraulic circuit. So I have here a pressure source. This one here is a pressure source. Then I have a direction valve that is having the operation condition as it is shown here. This, by the way, this direction valve has a three different operation conditions. The one that I'm connecting lines like this, the one that I'm making them to be crossed, and the one where things are completely closed. Okay, now when the line is connected here, when the pressure source is connected to hoses with something, this valve here is called counterbalance valve. Can I make an assumption that the pressure here, this point, is same that the pressure here in this point? Yeah, it's a fair assumption because typically the hose lines, there's nothing that introduces the pressure losses, so it's okay. Of course, if the pressure line becomes to be, the hose line becomes to be extremely long, then they might introduce a little bit of pressure losses, but generally speaking, they don't. They don't, because the hoses are made big enough to make sure that you are not losing your energy. Pressure losses is always equal than energy losses. Okay, then we come here. Can I make an assumption that the pressure here is same than here? Is it going to be the same pressure? No. No, because a counterbalance valve can have an operation condition as it is shown here, meaning that the line is completely closed. Nothing gonna go through it, and this is one of the typical examples about variable diameter of throttle. So how much flow is traveling through here depends on the drillings, and depends on how it is measuring the pressure here, how it is measuring, there are different kind of pilot drillings here. So it's balancing the spool position based on the pressures in different locations of the hydraulic circuit. But what is important is that the pressure here is different than pressure here. Okay. Now I got the pressure here. I think it's going to be same here too because there's nothing that introduced the pressure losses. What about this pressure here and the pressure here? Is it going to be same? Absolutely not, because they are not even connected. No connection whatsoever. No physical connection. Mental connection here is not accounted. So it's physical connection that you must have. Okay, then it's going to be hose line all the way here. So I think that I can have a fair assumption if I say pressure here, same than here. Shouldn't have any pressure drops. And then you take this in a pack in a pump, tank. So to compute this one, you need to have a differential equation here, which corresponds this area. You need to have a pressure here, which corresponds this area. You need to have a pressure here, which corresponds this one. Force produced by cylinder will be pressure here multiplied by corresponding cross-section area of the piston. Pressure here minus pressure here multiplied by corresponding cross-section area. Makes sense? So again, what we need is just to get this differential equation to compute the pressures, nothing else. And then we're ready to go. We're good to go. So what do you guys say? Makes sense? In land fluid theory, hydraulic system below can be modeled. Here are the choices. So this is one-way cylinder. It's a one-way cylinder where there is a fluid only in a piston side. Piston rod side is assumed to be not pressurized. It's not assumed to be no fluid whatsoever. So is it going to be something like shown here, like we looked at in the previous example? Is it going to be something that there are two volumes to compute right after the pressure source? There's a pressure source, or is it going to be just the one volume after the there's a direction valve, or is it going to be a total of three volumes after the direction valve? Which one is correct? Oh, it's not on. Okay, okay, sorry about that. Uh, Next. Okay, we got 225 students. So the last ones is only, what is it, six? Six of you decided this is no longer me, that I want to be a part of this class. I don't think that's very bad when you look at the percentage, because usually the dropout rate is much bigger than that. I don't know what's the usual dropout rate, what comes in the lectures. People usually follow, with the first lecture, that how many people participate is 100%. Next lecture, I think it is like, how much? 75, 50, 25, 0. That's a standard thing. So we still have a very high percentage. Oh, yeah, this is, you cannot see this. Okay, sorry about that. Let's take a look at this. And here's my proposal. Let's look at this in-class quiz, and then you're going to make a break. And after break, we can do one thing only. We're going to take a look at the line fluid theory. And that's going to be your differential equation. This is what you need to understand. You need to understand how it behaves. Otherwise, you have no hope. Okay, what's the WhatsApp community saying this time? C. C. No comments from my side. C. Oh, yeah, C. Hmm. But there's a not, I feel, a certain level of uncertainties here. Is it now? Is it clearly C or something else? Okay, what do you guys say? Let me take this one. No, where is it now? It's this. Where is it now? Here. I put it in a side like this. Okay, we got 105 answers already. 106. Last time I think it was 114, or what was it? Roughly that much. And then 110. So I think that we are pretty much there. So I'm gonna close this momentarily. Okay, guys are still thinking, is it making sense to vote? What? How are you gonna vote? How are you gonna cast your vote? You ready to cast a vote? You're done? Okay. Okay. We got all the answers. So correct answer is, of course, C. Oof. Ah, this WhatsApp system is killing me. This is not, this is, what if who's going to cover it if I'm going to get the heart attack? Is it going to be WhatsApp community? I don't think so. They're going to be just having fun with a high score, and they don't care about the consequences. This is really hard to my heart. Okay, guys, here's what I'm proposing. Let's have a break. Are you comfortable with the 5 minutes only? 5 minutes only. You're okay with the 5 minutes? Okay, 5 minutes, and then we will be back. Line fluid theory. We're gonna wrap up the things. We're gonna go back home, enjoying the fantastic weather out there. Too bad that they said that it's gonna be plus temperature. It's not gonna no longer sub-zero end of the week, so we're gonna lose in the snow. Very, very bad. Okay, guys. Okay, so we just discussed about the digital hydraulics. So what's the deal with the digital hydraulics? We're gonna get back to this next week. But is it so that none of you have ever heard about digital hydraulics? Even Team Finland have not heard about the digital hydraulics. Are you guys serious? Okay. All right. So I'm gonna tell you what's up with the digital hydraulics next week and why it makes sense. Because it makes sense. I mean, there's a there's a big promise. Let's put it this way. There's a big potential. And the big potential because the hydraulic circuit always works like this. Let me take myself back where you were. So typical scenario of hydraulic circuit is that, like pretty much shown here. Okay, I got the message. Yeah. Okay, so let's ask. So he's alive. Okay, so let's see. Okay, now typing. But where the heck is the results? Now we lost the results. Can we go back here? Ah, we don't have it anymore. Oh God. Show the results. Where they show the results? There. Show the results. 100%. Oh, this is what we need to show to him. If he say yes, but if he's saying that, no, he's thinking. Okay. This seems to take forever. Thinking. Is what? Oh yeah, his face is missing. That is correct because I did not put my camera on, so I'm back here. So let's see if we're gonna get this. No, not responding. Please, Juhis, say that we can call you. Uh, oh, there's this way that I can have also this FaceTime. FaceTiming. Okay, he's not playing with us. I see that. Okay, what are you gonna do? All right, but I was about to explain this. You know what you do in hydraulics is that you always have a like reserve of energy because you might or might not need it, and that's what the hydraulics is based on. It's like there's always a little bit of excessive amount of energy available. Uh, okay, okay, so he's let's take this back. Okay, FaceTime. I don't know if you guys can hear this. No, not responding right now. Hello. Here's the deal, boss. So I'm here in the lecture with 128 students, and we've been, thinking, what if we're gonna have an in-class quiz, and if we're gonna score 100%, meaning that every single one can answer this question correctly, what we can do? And they say, you need to call the rector. That's exactly what I'm doing here. Look at this. I don't know how well you can see it, but it is 120 7 students, each of them scoring 100%. And we are here and online in YouTube. So you want to say something to our students?
Excellent, absolutely great record. How did you do that? Of course, not because of the students, but
Because it's because of the best students. It's not because of me. But look at these guys. They have very big brains.
yeah, that's more than excellent. Yeah, as a university, we are doing quite well despite of the rector, and I guess you are using the same methods there. So excellent students,
That's
excellent
exactly what we
students.
do. So just want to say you hello, and these guys want to say hello. They have a very big brains. Next time we see them in a corridor, we need to make sure we salute them because of the high score.
Yeah, excellent work, excellent work. And then thank you for calling. As I mentioned, I'm eating my kebab.
So he's eating his kebab. Very nice.
Yeah, it's an excellent kebab today, I would say.
Okay, you
Okay,
enjoy your kebab. We continue with our hydraulics.
okay, thank you.
Thank you,
Bye.
Juhis. Bye.
Bye.
Okay, so I made it as promised. So what do you guys think? Cool. I think so too. Look at the rector is answering. He's almost, it's already more than a 5 o'clock, so it's no longer office hours for sure not. Oh my God, a special lecture today. Very special one. Okay, but next we need to do this. We need to get back to this. So this is what we're gonna take a look. We did that already. Okay, so here's how we're gonna derive this first order differential equation. This is not gonna be too complicated at all. So what we need to do is that we need to start looking at the control volume. There's a volume where we're gonna focusing on. And when you look at the volume, there is a mass flow that is coming into the control volume. Mass flow is going to be equal than the density of the material that is coming in multiplied by the flow rate. How much material is actually coming in, and then how is the density. The material flow leaving is going to be the same, except that it is associated to mass flow leaving out and the density that is corresponding to the material that is leaving out. The ones that is within the control volume is this one here. So that's what's going to be within the control here. Now, what we need to do here, we need to look at how much is a mass within the volume. That's simple. So we just need to know the density of the material we have there and the size of the volume. That's clear. That's what we learned already when we look at the multi-body system dynamics. So no difference whatsoever. Now, how is it we can change the mass here? Now, because here we actually can change the mass. How we can do it? So if the incoming and outgoing mass flow is not going to be equal, something is going to happen. If there's more stuff coming in than leaving, mass is going to increase. Another way around, if there's more stuff leaving than coming in, then it's going to decrease. So that's the way we can play with the mass, because it's a mass that is within the control volume. So the mass change is about how much in, how much out. It's a simple thing like that. Okay? Now, when I'm using this previous notation about the mass flow, and when I'm using this density multiplied by volume as my mass, then I can write the equation like this. Okay, now I have this differential operation, so I need to differentiate with respect to time, density, and the volume. Density and the volume. Okay, and then here, this side of the equation have no changes whatsoever. So when I do this differential operation, I have here density change as a function of time. Volume change as a one function of time. And when I do this operation, when I'm using the assumption that the density of incoming and outgoing material is same, which is the same, because if we're speaking about the oil, the density is not going to change radically, at least not radically. So we can make a safe assumption that density is all the time same. So when we do this kind of assumption, we can write like this. We are not yet there, because look at, we still have a density that we are playing with. So we need to make more information. And we can use this relation that is, coming directly from the math, density and the volume relation. And once we're using this kind of the relation, so this is basically saying like, dV divided by, it's actually like dP, so it's going to be volume versus pressure. It's going to be like this. So this is what is essentially saying. So once we're using this definition, along with, again, the friend that we learned already a week ago, which is a definition of bulk modulus, we can write this change of the pressure, change of the density as a change of the pressure. And now we become to be very close where we want it to be at. So this is how it's going to be written. And now when I'm moving everything except this differential operation in the right side of the equation, here's my first order differential equation. This equation says this, P dot, which is not the pressure, but it's a P dot, which is not a big problem for us because from P dot we can integrate P, okay? And from P dot, it can be written as effective bulk modulus divided by volume. Then there is a flow rate in, flow rate out, minus change of the volume. Change of the volume is like when you have a hydraulic cylinder, the particular like in a piston side, you can have this volume that is changing radically depending where is a piston position. So that's how you can actually compute the pressure at any given time. What do you need to know? Of course, you need to know this effective bulk modulus, which is describing flexibility, like we all know that. Every single one of us knows that, including the rector knows it. So we're safe. So we know what's that. This is a volume size. We know that too. This is a flow rate in. We have not discussed about the flow types or the volume flow itself, but that's flow rate in, flow rate out. And how is that we can change the volume? How is that change of the volume, how that can be taken into account? That's it. Now we have a first order differential equation, and that we can use for every single one of these the volumes where they're, how we're gonna, once we discretizing our hydraulic circuit. How you guys think about this? Not bad. It wasn't bad at all. There's something that the Flamm fluid theory is not taking into account. Pressure waves, is that something that is not accounting? Size of the hydraulic volume. Look at. I'm gonna write this equation one more time. So I'm gonna write this equation like P dot going to be. You guys missed it big time because we just called the rector, and rector wanted to have a list of the names of all the participants, and you guys were not here, so you're off from the list because he want to come and hug you. Okay, so it was like, let me get back to this one. And then there was an in, out, and then let me explain one more time. Flexibility, volume difference, volume change, flow rate in, out, that's it. So one thing is not mentioned. Which one is not mentioned? What is that? What sub-community is saying? A, pressure waves. And is it come with 100% certainty or little less than 100%? Is what? Ah, okay. Discard. So the Socrative is not open, but it's going to be open. This is what we did already. This one. Okay. So is what? Ah. Okay, so it's 90, 100%, 105, 100, not 100%, 100 participants, 110, 14. So you guys think it is 100% again? No. Is what? We'll see. We'll see. How we got 115 answers, 99%. How come, is it, people can join in this WhatsApp community? Is it like you voting first in a WhatsApp? Or somebody just saying, I know for a fact that it's going to be B, and then others are following? How it goes? Ah, okay, okay. That's what that what it's like. Want to be a millionaire? This TV show. You can ask from the audience, and the audience saying, okay, material is voting for A or B or something, and you just follow the crowd. Oh, okay, makes sense. Makes sense. Okay, we got 100. Oh, look at this. So we back where we were. So we got 120 something, almost 120 answers. That's really good. That's a good sign. That's a good sign. 120. Good. So we're gonna show 100% yes or no. Yes, no. So it's yes and no. Is most of you are saying no. Okay. Let me take a look. Ooh. Oh my God, this is, I need to figure out something else because honestly, I think the rector is willing to play with me once. But if I keep on calling him like, a couple times per day, soon he's going to say, okay, not cool, come to see me in my office. All right. Thank you, Mustafa, for voting incorrectly. Yeah, exactly. Oh, okay, this one. Now I got the more energy. I'm not feeling that much tired anymore. So I'm gonna still, even though that I promised, I'm gonna still briefly. This is annoying thing. So this is what they would like. I think that they should fix this because now I need to do this, and then I need to do that. Ah, why? It's somehow like it's displaying incorrectly. No, what is that I need to, because I need to change the settings here. So is it Windows what? P. Windows P. What should I P? So it's a duplicate. Yeah, P. Okay, so it was a duplicate. So now it's okay. All right, last matter to discuss, because we covered the lamp fluid theory so fast. So it's gonna be flow types, different kind of flow types. Okay, so we have, like mentioned earlier, so we have laminar flow and turbulent flow. And they're not going to change from one to another like just like that, but there's a phase that is unclear what it is. But these two flow types, they are having the completely different behavior. Why it is doing this? Now, again, I need to get started from scratch. Okay, how it look for online participants? It's good? Okay, I just need to make sure that you guys see this well. Okay, we all good. No, it's back. It's back. Okay, good. All right, so I'm saying that there are two different types of the flows, and their behavior is completely different. And they're different in a sense, like how the particles, these famous particles, how they are traveling. So in a laminar flow, which takes a place when the pressure difference is small, traveling is like this. So if I have a throttle here, so there's a pressure here, and the pressure here. So the pressure difference can be computed in simply like P1 minus P2. So it's not too complicated. In a case of laminar flow, the particles that are fluid particles, they're traveling with a good order. So they have no disagreement whatsoever. So they go like, the particle is here, so it goes like here, and it's going smoothly. So there's a smooth traveling. So there's a well organized, there's no traffic jams, no accidents, no collisions, everything goes smoothly. That's laminar. That takes place when the pressure difference is small. But as soon as the pressure, as soon as the P1 has started to increase, then this particle becomes to be in a hurry. And when they're in a hurry, you know what happens when you're in a hurry? You have like traffic here, you have 4 lines here, and then it goes down to the 1 line, and every single car wanna go same time to this 1 line. There's gonna be a lot of accidents, a lot of whirlings. It's something that if the particle is traveling, then it's gotta be like this. This is called whirling. It's still not the rotation of the particle, but the particle go in a whirling path. That would happen. And this is a typical scenario. This is when the pressure is high, because they are so much in a hurry, so they are no longer capable to do things in a good order, but every single particle want to go in the same time, is not physically possible. And because of that, the whirling takes place. And this is the case when the pressure difference becomes to be high. Okay, what's high? What's low? Roughly speaking, this kind of the type, which is the laminar, takes place when the pressure difference is less than let's say I'm saying like 2 bars. 2 bars. And more than that, it's going to be turbulent. And of course, it's not going to be just like first laminar and then turbulent, but there's a certain region that is unclear what exactly it is. But there's a number that helps you to define what it is. And this number is something that I'm sure you have seen this before. It's called Reynolds number. Reynolds number. That's what it is. Okay. I don't think we really need to use this, but for your information, if it is unclear what is what, if it is a laminar or a turbulent, this would be the way to compute it. For modeling perspective, typically what we do is that we simply assuming everything to be turbulent. Turbulent comes with the one big numerical problem. And the big numerical problem I'm going to explain to you later. So in the numerical solution perspective, it makes sense to model the region that is close to the small pressure difference to be laminar. Not that it's really making much of a difference in terms of performance, but simply because it's just more pleasant in terms of computing. Okay. So I was about to explain this. So there's a very unclear notations because Reynolds number is a function of what? This is kinematic viscosity or velocity. Which one is what? Okay, and multiplied by something that is called hydraulic diameter. Hydraulic diameter is typically not the physical diameter of the throttle, but something you can define otherwise. And then this is a velocity. That's how you can define it. This is how you compute the Reynolds number. Then you compute whether or not there's a less than something called critical Reynolds number or more. If it is less, then you can safe to say that okay, this is laminar flow type. If it is turbulent, is it going to be then the number is bigger than the critical? This is confusing because it gives you the answer that it's either or, and it's not like that in reality. There's like area that is both or combination. Let's put it this way. But that's okay because in a modeling perspective, this is a minor detail. Doesn't make much of a difference. All right, here are the 2 types. What it makes a difference for us as a modeling perspective is that in a laminar flow, the pressure difference and the flow rate, so how much material is coming through this throttle, they are linearly related. So there's a linear relation. And this linear relation is defined by a coefficient that is CL. How you can get that? You can get that from pre-calculated tables, but what matters is that this relation keeps on to be linear all the time. So that's what matters. That's something that is good to keep in mind. Now, let's look at a little bit about the examples. Here are the few different kind of the drilling systems. And of course, it's complicated equations needed. Don't get confused about that, because eventually what matters is this relation. This relation is linear. So if you make a plot such that this is a, let's put this as a flow rate, and this is a pressure difference. So it's like this. This angle is defined by these numbers. What are these numbers? Well, of course, they depends on what kind of throttle you're dealing with. This is something that actually looks very, I don't know how you can manufacture rectangular throttle. Because this is a rectangular cross section that is having a length of L. What kind of drilling system you can use to make a rectangular hole? I don't know. A little bit theoretical, I would say. At least I'm not aware of how you can drill the rectangular hole. Do you know how to do it? Because I don't think you can do that in the real life. But anyway, so you do? You know how to do it?
Yeah.
How?
Through that electro EDM spark machine.
Ah.
A copper electrode of rectangular size.
Okay, let me correct. I don't do how to do these rectangular holes in my garage. You can do that if you have a machine shop, but in my garage, I don't have a device like that. But I have a lot of different tools, but not the one that can make a rectangular drilling. Okay, but I can make a circular shape. That I can do. That's not a big problem. I can have my drilling system that I can make this. And if you have a circular shape, it's going to be a diameter, power 4, and so on and so forth. None of the stuff matters. What more matters is this relation. That's what is very, very important. This relation. Look at, we have this good friend of us, the one we met a little while ago, viscosity. That's part of the game. So viscosity makes a difference, but only in this case. Only in this case. Okay. Here's a more example. Again, in my garage, I don't have a device to do this. Do you? And when I'm thinking that if I drill this like circular, like rim shape, what's going to happen? The middle part. How can I keep the middle in a place?
Go down.
It's going to, what? Is what?
Oh, it's like drop down.
Yeah, it's going to go away, I think. So I don't think that this is well designed. But anyways, that doesn't matter. These are coming from pre-calculated tables, so no, let's not look at how you can do this in reality. That doesn't matter. Okay. Next, turbulent flow. Turbulent flow, again, what is important for us is relation. Flow and the pressure difference. Quadratically related. Quadratically related. This is important for us. So we see that, again, let me make this drawing. I'm thinking I make a drawing in a way that it's going to be pressure difference this side and the flow rate this side. So this is quadratic curve. So it's going to be like second order curve, like this. Okay. I mentioned that there's a mathematical, let's say, numerically this is unpleasant. And why this is a little bit unpleasant? Because we're doing the prediction based on tangents. Tangents that are clear, so it makes sense. But as soon as you're approaching the position where there's a zero pressure difference, then of course the flow rate's supposed to be zero too. But as a prediction is based on tangent, so the tangent here becomes to be infinite. It's not able to understand well that the pressure, when the pressure difference is zero, the flow rate is zero too. So that's why actually it makes sense that when the pressure is small enough, let's say 2 bars, then from this point you take a linear line here all the way to the origin of the curve, which is a zero pressure difference, zero flow rate. So it's like bilinear. So this is first the linear part, and this is quadratic part. Not bilinear, because bilinear would be two linear curves, but I don't know what that is called in any language. I don't even know how that is called in Finnish language. But this is a linear, this is quadratic. And this simply because the prediction when the pressure difference becomes to be small is more handy. So it's more pleasant. Okay, but again, what we need is this relation. It's a quadratic relation. in a turbulent flow. Okay, guys. So what do you say? Now, here are the parameters needed. There's a discharge coefficient. This is something that you need to, this is not actually very simple to compute. There's a cross section, there's a density of the fluid, that's okay to compute. This one is a little painful to compute. This one particular is a little painful to compute. And that's why we are not going to use the equation like this, but we're going to use something that is called semi-empirical modeling approach. Guess what? Guess who is a father of the method called semi-empirical modeling method? He's a professor in this university. He's a professor in the best department in this university. He's a professor. How can I give you more hints? He's a Heikki Andrews. Seriously. He's a father behind of this. Yeah, think about that. So he's a like forerunner in modeling of hydraulics. So he introduced something that is based on semi-empirical approach. Why? Because it's okay, it's kind of doable to get all these parameters. But in the real case, the needed, parameters you really need becomes to be huge, enormous. And some of the parameters you don't really have an access to, even though that they're seemingly simple parameters, but you still don't get an access to that any other way than taking the real components, cutting that half, measuring the components, but it's a little bit against the concept of virtual design that you do nothing in real life. Particularly, it's not a good idea that you purchase a brand new component and the first thing you do is to destroy it. Not a good idea. So he created a method that these parameters, all the unknowns, can be obtained from simple measurements. Something that they are kind of combined, and you can get from manufacturer's catalog. Because manufacturers are telling a little bit about the features of the components, and that's where you can get an access to these components. You don't exactly know what is what, but that doesn't matter, because what matters is that is it this relation between the pressure difference and the flow rate linear or nonlinear? If it is nonlinear, these parameters can be updated in a certain way. What is this way? That I'm about to tell you next week. So story continues. So with that, we're going to close for today's lecture, and we're going to see you guys on Monday. What about this career counseling? Yes or no? What are the online participants? What they saying? They say, they don't say, can you see that from YouTube? They say nothing. I'm going to take a look at it. They say okay. They say, why not? So they say yes. Okay, career counseling will be the closing thing, but it's not going to be related to midterm exam. Okay, guys, go home. See you on Monday again. They say yes. Good.